Hello and welcome to our Domain 3 lesson. Once again, this video is intended for those of you who've been studying the material since before May and are about to take the CISSP exam. This video should help you identify what's changed, or rather what's new in the common body of knowledge. As I said in one of my other videos, there isn't a whole lot that came out of the common body of knowledge, but there's a whole lot of new stuff. So without further ado, let's dig into Domain 3 terminology. The first concept is secure defaults. This is also known as restrictive defaults, and I'll say this again for those of you who are new to this channel. Basically, ISC² loves to use these AKA terms in the exam, or the thesaurus terms, so you could see either of these appear on the exam. So it's important to pay attention to the various interchangeable terms that you're going to find throughout your books and as you study the material. So secure defaults from a manufacturer's point of view means that our products are securely configured as shipped, meaning you don't have to apply a lot of configurations out of the box. The product or software is capable of preventing breaches from the get-go. It also means that it should initialize or start up in a secured state. It also means that during any unsuccessful initialization, it should still perform actions in a secure state or not perform actions at all. So before we get into the next slide, we need to have an understanding of ISC²'s official definition of failure, which is basically an action or a behavior that deviates from the documented or expected behavior of some component of the system. Fail securely. This basically means that failure of any of the following should not result in violating a security policy. Failure of functions, failure of mechanisms, and recovery actions mentioned here. This isn't saying failed recovery actions, but instead this is talking about how recovery actions themselves that result from a failure shouldn't cause a violation of security policy. And this is discussed in NIST 800-160. Another concept is continuous protection, which means that a system can reasonably detect actual or impending failures during initialization, normal operation, shutdown, and maintenance. It also means that it can circumvent any failed component by reconfiguring itself, completely shutting down, or revert to a previously secured version. And that includes rollback. The best way to explain keep it simple, first of all, it's also called reduced complexity. But the wisdom you'll need here is to understand that a simpler system results in fewer vulnerabilities. It's also easier to verify security policy implementations. This also gives you better assurance on vulnerabilities, meaning whether they truly exist, whether they're correct, and whether they're complete. Zero trust is an architecture in which nothing is trusted, just like the name implies. Devices and users need to be authenticated and authorized for each and every action. An example of this could be where you require your users to authenticate when they first arrive at their desk. After that, another login is required to access email. After that, another login is required to access network folders, and an additional login required to access each separate subset of folders. After that, another login might be required to access the mainframe, and so on and so forth. The levels in which this type of policy is implemented needs to be well documented and well governed. So be thinking about zero trust in the context of things like change management, baselines, and security policies. Privacy by design, there's just a little bit of information on this, but basically ISC² wants you to understand that privacy by design should be implemented throughout the entire SDLC, System Development Lifecycle, or Software Development Lifecycle, and that it needs to be collaborated and communicated at all staffing levels throughout the project. Trust but Verify has two additional names to be aware of, as these could pop up in your exam: System Assurance and Security Verification. What this boils down to is a process of looking at and looking for the presence of proper behaviors against some type of measurable criteria. The same would be said for the absence of improper behaviors. And one of the keys here, again, is measurable criteria. An example would be to monitor the CPU usage of our servers to make sure they're within a certain percentage. Another might be to monitor config files to make sure that there aren't any changes made. Shared responsibility is the same as the name implies, but it's in the context of design components that are shared during the design of a system. ISC² only mentions security logging, specifying the user groups, and testing in non-production environments. Moving on to microservices, these can be thought of as a collection of services that communicate with each other. They use a standard communications protocol. They have well-defined APIs and they're independent of vendor product or technology. And microservices are built around capabilities. For example, if you wanted to build a mobile phone application that connected drivers and people who need a ride, and then collect a fee from the rider in order to pay the driver, you might look into what microservices can be gathered to create that application. And basically that's what Uber is. And microservices are deployed inside application containers. So what is a container? So if you're familiar with virtual machines, you know that they tend to use a lot of resources. Containers are virtualized at the operating system level instead of the hardware level. If you're not familiar with this, the best way to think of it is that VMs are basically slicing your hardware into separate pieces, reserving memory and such by running separate operating systems within the VM, whereas containers are using the same underlying operating system of their host, and that frees up some resources. So they're still slicing and dicing, it's just the operating system is the one that's being used overall. I'm not sure if I explained that. So yeah, it sits on top of the same kernel. They're done at the operating system level, again, meaning that the specific portion of resources is freed up to allow more containers than a VM would allow. And so they have their own process ID lists, network devices, and file system user lists. And here are some examples you might be familiar with. LXC, OpenVZ, Parallels, Virtuoso, Solaris containers, Docker, and HPUX containers. VM sprawl is a new term that basically means an administrator has lost control of all the VMs on a network, which jeopardizes all the services offered. So a bit more here on containers, and this will be especially useful for those of you who are new to these subjects. Container and application container are basically the same thing. This slide just gives you the added knowledge that this other term you might encounter, OS virtualization or operating system virtualization, is basically where the application is given a virtualized view of the operating system. Don't confuse this with virtual machines. There's something called a runtime engine that allows the container to talk to the operating system. And the result is that the applications are abstracted from the operating system and are isolated from each other. Moving on to serverless cloud computing. This doesn't actually mean there isn't a server, so don't be fooled. This is where the customer purchases a cloud service based on peak, seasonal, or on-demand services. Don't confuse on-demand with something like pay-per-view. The quote-unquote on-demand we're talking about here is for whenever your services might be in the highest demand, for example with Netflix or Apple TV. A serverless approach might work based on evenings when their services are in highest demand, or if, for example, you're running a tax preparation service in the United States, April through July might be your busiest months, so you might consider a serverless architecture for your site. High-performance computing systems refers to super high-speed computers. These are used for basically big data or data analytics to look at things like buying patterns of individuals so they can be sold to retailers. HPCs are used for cryptography, hacking, and cryptanalysis. ISC² talks about vulnerabilities and mitigations for HPC. Latency constraints, from what I can tell, refers to quote-unquote normal tools being too slow to interact and that the latency cost is too high. Improper workloads refers to when or if the HPC is compromised, resources are constrained, which is true for any system, but I guess what they're alluding to is that these systems are usually unprotected. So if you know from firsthand experience, let us know in the comments below. We're just going by what the official training says here. Mitigations are having a good architecture that uses enclaves, for example, placing detection tools at the perimeter instead of host-based IDS, IPS. For logging and monitoring, you have to consider the trade-off between resource use and accountability. And then, of course, you need to have a log review and monitoring process in place. Edge computing is where a layer of computing is put at the input source. For example, the layer can be an embedded device, such as an IoT fridge or an IoT thermostat or cooling system. I'm sure you've seen Nest, and some of the Samsung fridges out there have IoT devices in them. I don't know if those are exact examples of edge computing, but something to kind of illustrate what they're talking about here. Fog computing. Try not to confuse fog and edge computing. NIST 500-325 talks about the differences, but don't bother reading it. Just like all NIST publications, it'll put you to sleep. The key difference between edge and fog computing is where the computers or where the computations are done. So just remember the phrase, Edge is embedded, fog is further. So you've got a multi-layered architecture. Computations are not done at the physical source. They're not done at the cloud either. They're done on some other device. From what I understand, the purpose of both of these is to reduce the computational cost of the cloud servers. Here are some edge computing vulnerabilities and mitigations you'll need to be aware of. These aren't anything new. It's mostly just applying wisdom to the edge computing concepts. You have these two vulnerabilities: network compromise, which includes denial of service and disruptions to the connection. And you also have the increased attack surface just by having so many devices out there. Mitigations, of course, would include monitoring, a solid incident response process, and a solid inventory process to help reduce the possibility of rogue devices or misconfigurations. Getting into hypervisors, if you've been studying, you should already know what those are, so we'll just jump into the added material here. Type 1 hypervisor has Type 1 security. I don't know if this is significant, but at least the numbers line up. Key points here are that Type 1 is running at the hardware level and has a lower attack surface. With Type 2 hypervisors and security, we have them running on the operating system, which means there are more vulnerabilities and that it's more attractive to attackers. Getting into key space clumping and clustering. This one threw me for a pretty long time, and please, I invite anyone to chime in if you have experience or knowledge about this. Key space clumping or clustering is a technical term, I believe, that has to do with keys being non-randomly generated. The training materials were pretty scant on this, sadly, so unfortunately I can't give you a whole lot more. Please be aware that the term clustering in general refers to the different keys producing the same ciphertext for a given algorithm. You may or may not get a question on this. I'm just here to kind of give you what's new on this. So once again, key space clumping is different than, and key space clustering are different than clustering in general. So keep that in mind. These have to do with key generation, not being as random. When you're clumping, I guess it's not as random or something like that. Moving along to pass the hash, it's kind of a tongue twister. This is an attack where the user's password hash is obtained from a device and sent to the server for authentication. Since the authentication servers don't actually see the password, the hash can be used to gain what's called lateral access if the account has admin rights to other devices. Moving on to the three-headed dog. This came out of the common body of knowledge for a while, but now it's back in, so we'll need to understand it. I'm going to cover this quickly because of how much new material is in this domain, and this video is probably getting long, so please bear with me. The three heads are the three systems. We have the principal, we have the requesting system, which is the KDC, which has the two servers or services, the authentication service and the ticket granting service. And then we have the destination server, which is the application or file servers. Tickets are encrypted with symmetrical encryption, and the key distribution center has the symmetric keys. The way this works is that the principal or user logs into the key distribution center. Basically, your password hash is sent to the KDC, which after verifying sends you a ticket from the ticket granting service. And these tickets are used to establish trust on the network. So some more tidbits you'll need to know about Kerberos. Basically, the accounts expire after 30 days if they're not used, and that's when the accounts become untrusted. Not the tickets, the accounts. Again, the hash is the unique user key. After the authentication to the KDC, or the key distribution center, the authentication service, the ticket granting ticket is sent to both the user and the ticket granting service. And I believe the ticket granting service and the authentication service can sometimes be on the same server. Hopefully some of you with experience on that can verify in the comments. Ticket granting ticket lasts 5 minutes to prevent replay. The ticket granting ticket is encrypted with a symmetric key that's pre-shared between the authentication service and the ticket granting service. So the ticket granting service issues a session key that's encrypted with a different key, and that different key is only known by the ticket granting service and the resources or the servers that you're trying to access. Let's see. So tickets are kept in something called the Kerb tray, which is a non-pageable area of memory. And lastly, Kerberos itself doesn't encrypt the transmissions. I believe that some implementations can do that, but ISC² is saying that it's no good for securely transmitting data. So remember, only the session ticket is the thing that's encrypted. A few more final thoughts on Kerberos exploitations and drawbacks. As I said in the last slide, the tickets are encrypted with a symmetric key, but the initial and subsequent transmissions aren't, other than the tickets. So you do need to consider something like IPsec or MACsec. This presents a possibility, I'm assuming, of hash sniffing. and I believe this would also relate to pass the hash attacks. You also have denial of service attacks, basically flooding the servers, and this can be mitigated with something called rate limiting and throttling. With brute force, the keys themselves can be brute forced. So the mitigation to this, of course, is having longer keys. Kerberos is also susceptible to password guessing. So in order to mitigate that, you'd have to apply clipping levels or thresholds. And the KDC can be a single point of failure. So be sure to have it addressed in your backup and recovery plans by having a failover KDC. And lastly, Corba does support Kerberos. Moving on to ransomware, the new material on this talks about how your organization needs to consider whether you would pay the ransom or not, and that decision and other safeguards need to be covered in your business continuity and disaster recovery efforts, and that they need to cover situations where even your backups might be unavailable. Moving along to some more random tidbits that they've added. A little bit of an expansion on elliptical curve. Basically, it provides more security than RSA with a smaller key. We have something called bulk encryption, and this is the same as link encryption from domain 2 and domain 3 actually. They mention it in both. And this is also called point-to-point. So bulk, link, and point-to-point are all the same thing. So be sure not to confuse that with end-to-end encryption, because end-to-end is where you have a client and a server communicating. And then with link encryption, you have all the nodes. The nodes are the things that are encrypting. Digital envelope is basically saying, or basically using a public key to encrypt a symmetric key for secure transmission. And distributed ledger, domain 3 briefly mentions this in the context of blockchain and how there's a decentralized register and that multiple systems need to agree on a transaction before it's confirmed. And there's not really a whole lot on that, so unfortunately, that's all I got. Some more domain 3 topics. We have Crypto Suite Management, which is a cloud key management solution that has two different approaches. Remote key is where the key management server is on-prem, and the processing and hosting is done at the cloud level. Client-side key management is where the key management hardware and processing is on-prem, but the storage is in the cloud. The way ISC² presented this is kind of confusing, so if you have access to the self-paced training or the official student guide, I recommend looking this up on the Cloud Security Alliance's website if this explanation here isn't helpful. So yeah, I apologize for the way that these bullets are disorganized a little bit here. Moving on to CPTED, I guess that's how you pronounce it. This is an approach to crime prevention through the use of common sense tactics, such as placing receptionists or guards near all entry points, locating server rooms off the beaten path, and having thick brush near an entrance that you don't want people to wander into. It has three categories. It has organizational, mechanical. An example of this might be, okay, so we have the guards, and then with mechanical, you're going to have something like, this might be putting turnstiles at each entrance, or some new terms under this category are also contact devices or switches, which are remote control devices. Solid core and hollow core. Solid core refers to a thick and heavy door, whereas hollow core, of course, is a super light, easily breakable door. You have things like a man trap, which is, where only one of the doors can be opened at a time on two ends of a passage or a chamber. And natural design, this might be the part where you're having the thick shrubbery or the dense bushes coating the path to a restricted entrance. Moving on to SCIFs, or Sensitive Compartmented Information Facilities, and this is basically a sophisticated way of saying a restricted work area. And some key differences might be having soundproof doors, or basically a solid core or stronger. Should have its own power and telecommunications connections, as well as security systems that are separate from the enterprise. The rest of this list is pretty self-explanatory. Radio frequency protections might include something like a Faraday cage. They recommend not having windows, and monitoring motion intrusion detection, cameras, things like that. With HVAC, we have some new additions. Sensors are recommended to detect things like overflows and leaks with notification mechanisms. We have this standard by ASHRAE for data centers, and it's worth noting the recommended temperature range for hardware, 64 degrees to 81 degrees Fahrenheit. And then we have the Celsius there as well for the best hardware life, and they recommend having 3 sensors at the top, the middle, and the bottom of a rack. Moving on to fire prevention terms. Getting into the new stuff, we have ionization, which detects smoke by measuring the electrical current between 2 charged plates while air passes between them. Photoelectric cells measure changes in light caused by the smoke particles. We have something called spot type detectors, which use a bunch of sensors, both ionization and photoelectric, and includes carbon monoxide, heat, and flame detectors for a wide range of detection and to reduce the false positives. You have something called VESDA, or Very Early Smoke Detection Apparatus, or apparatuses, I guess. So there's 2 alarm levels. We have low, which triggers an enunciator or a warning light, and then there's high, which would start the full suppression system. And these are installed in the plenum space. That should be a sub-bullet. Sorry about that. And then we have the classifiers. We have, which these have, I believe they've come back into the common body of knowledge. I think they were taken out. I don't remember them in the last main book that I had from ISC². So we have A for combustibles, Class B for flammable liquids, Class C for electrical fires, and Class K for cooking equipment. Sorry, did I skip D for flammable metals? So new to this area, we have Aqueous Firefighting Foam, which is a water-soluble foam for combustibles. In the category of non-conductive liquid suppressants, we have Novec 1230, which can be used instead of water, or the Aqueous Firefighting Foam for A, B, and C. And that wraps up all the new terminology for Domain 3. I want to thank everybody for sticking with me this far. If you have, if I put you to sleep, I apologize. It's a lot of material to cover in a quick time period. So I do recommend doing some supplemental research on some of this stuff. We hope to quickly finish our Domain 4 through 8 videos on this same topic. Other than that, thank you to everyone who has supported the site so far. Best of luck in your studies. Thanks again, and have a great day.